Let's look at some computer-generated slope fields and see what we can deduce about the solution function. So in these examples, you'll note that I don't even have any information about the initial value problem, the differential equation in general, and certainly I don't know a formula for y of t, but I can still glean some information about y of t. For instance, one thing we could look at here is if I said, suppose that we know y of 0 is equal to 3. Then what we can do is actually find the point 0, 3 and trace along these dashes to see what the solution looks like. Once I have that, there are a couple things I could look at. I could say that with this information, I would be able to answer what is the limit as t approaches minus infinity of y of t. Following along this pink curve, as I move toward the left, it looks like that's positive infinity. If we wanted to consider the limit as t approaches positive infinity for the solution function, here we see that it looks like we actually approach the value 2. I can also look at this and look for equilibrium solutions. Recall that those are constant solutions, one in which dy dt is equal to 0. And in talking about slope fields, dy dt equals 0 would result in horizontal dashes. So if I just look at this, I can see those horizontal dashes here, and that would have to be my equilibrium solution. So in this viewing window, that appears to be the only equilibrium solution. If we look at our next example here, I can see instead that there appear to be, in this window, 3 places where I observe horizontal dashes. And consequently, I would be able to see that this differential equation has equilibrium solutions at y equals 2, y equals 0, and y equals minus 1. I could also consider one question: what is the limit as t approaches positive infinity of my solution function in 3 different situations where I look at different initial conditions. So in each instance, what I'd like to do is think about the specific function that passes through that given point and consider what happens to it as I send t to positive infinity. So to begin with, the first one looks at an initial condition, let's say around here. And if I follow that to the right, because I'll point out we're only interested in looking at movement toward the right, this case we're looking at positive infinity for t, that appears to grow without bound. If I look at y of 0 equals 1 and follow that to the right, that appears to approach 0. And if I instead look at negative 1.5, we can see that that seems to approach minus infinity. So again, very different behavior based off of what we're assuming our initial condition is. Another thing that's common to do with these types of questions, we can consider what, if I have a collection of slope fields, trying to match those to an appropriate differential equation. So if I think about that process, then there are a couple things we can kind of do to structure this. So I would term this matching. So if we're ever in a situation where we're provided with some differential equations and some slope fields and we need to connect those, what you want to think of is checking some of the following conditions. So questions I would kind of ask myself, is the derivative dy dt a function of only y? In this instance, what you can think about is that means that the dashes don't matter with regards to what x is. So dashes should be identical along sorry, I didn't put this a function of only y along horizontal lines. So if I fix my value of y, I'm saying as I move along that horizontal line, I have the same y value, then every dash should be the same. If instead we want to think about is dy dt a function of only t, then in that instance, what you could think about is dashes should be identical along vertical lines. So again, the reasoning for that is because if I fix my t value and move up and down my vertical line, changing y should have no bearing on the dash for dy dt. The other thing that we saw that was kind of easy to spot if I had a computer-generated slope field is looking at where is dy dt equal to 0. So we can find that on the slope field, but we can also look at a differential equation and figure out values that cause that to be 0. So those are the main things I might look at first. Beyond that, and needing to further distinguish that, I might consider where is dy dt positive, because we know that we're looking for dashes that look like this. Where is dy dt negative, because we're looking for dashes that look like this. And then the last thing I might consider, if I had still some that kind of overlapped on all of those other categories, is you could compare, as we've noted before, the steepness of these dashes. And again, if we have something that's steeper, that corresponds to more positive or more negative with regards to dy dt. So with this in mind, what I want to look at is some particular examples. And what I'd like to do is, let's see if I can put those on here. Let me write here the 4 different differential equations. So dy dt is equal to y squared. Dy dt is equal to t minus 2y. Dy dt is equal to e to the minus 0.4t. And finally, dy dt, well, maybe I should stick with my convention of capital letters. Dy dt is equal to minus t. So if I take these 4 differential equations and these 4 slope fields, what I'd like to do is match them together. So there are different schools of thought or different preferences. Some people prefer to look at these slope fields and look for distinct characteristics. Some people prefer to look at the differential equations and instead do that. Doesn't matter. This is really a process of elimination if I'm assuming every single one has a pair. So one thing that I might look at to start with here is that there's only one that depends only on y. So depends only on the dependent variable. So according to what we said above, that means I should look for a slope field such that if I were to draw a horizontal line, every single dash would be identical along that. And this is also saying there should be only one. So when I start to think about here, you can draw a horizontal line and kind of look for that behavior. You'll notice that the only place that seems to occur is in the figure 3. So with regards to matching these, this looks like this would be A. That's the only one that demonstrates that behavior. Now I can kind of remove that from my list, right? We've already taken care of that one. Then I could think about the remaining ones. Both the C and D depend only on T, the independent variable. So dashes should be identical along vertical lines. I can see that that is true for 1 and for 4. Now, one big difference between those 2 slope fields is the fact that if you look at the dashes in 4, none of them correspond to a negative slope. But of course, you do see some negative slopes in 1. Coming back to these, this is always positive. And of course, for D, we can see that that's negative for positive values of t and positive for negative values of t. So that alone, I can see that this would be D and this would be C. Now, finally, of course, like I said, it is a process of elimination. So I would know that this is B. And notice some things about this. I can see that they're not constant dashes along vertical or horizontal lines. You can see that dy dt should be 0 whenever 2y is equal to t. And that's when y is equal to 1/2 t. And you can kind of see almost this like horizontal dash behavior along that. So that would be another argument in matching those if this wasn't what I left as the last thing to line up. But that kind of demonstrates a general process we could approach here with how to match a slope field to a differential equation. And again, the larger perspective in this particular video is realizing that we're probably not going to be spending a lot of time drawing slope fields by hand. What can we get out of that computer-generated behavior, especially if we had a very complicated differential equation where I couldn't solve it? Maybe we don't need to solve it exactly in order to get the information that we really need for whatever problem we're working on. And perhaps a slope field could be a way that we could get there.